because we're going to be a little short on time. So your homework tonight is to do a checkout. That checkout is on the first set of notes. So if you haven't watched that first set of notes, or like if you weren't entered in the Zoom meeting yesterday, then you may want to watch the Zoom meeting from yesterday. This warm-up is a great example of what you'll be asked to do on the checkout. So again, that homework tonight is on stuff we already did. We're adding in some new stuff today. That's like, I would say it's pretty challenging to keep straight all the different types of parallelograms that there are. I won't ask you to do anything on that tonight. We'll just continue with it tomorrow. So what we have talked about so far are general parallelograms. And so for our general parallelograms, we know a few things. We know that if I have a parallelogram and I'm told it's a parallelogram, then my opposite sides are congruent. And I know that my opposite sides are also parallel. Okay, so this side is congruent to this side and they're running parallel to each other. Same idea here. We know that our opposite angles are congruent. So the angles across from each other would be the same measurement. And we know that our adjacent angles are supplementary. The last property that we talked about with our parallelograms is that if I have diagonals, that they get bisected. So that this diagonal is cut into 2 equal parts. And this diagonal would be cut into 2 equal parts. So the diagonals are bisected. Okay, so that's kind of an additional property we learned. General parallelogram, all of this stuff is happening inside of there that we can use to solve for a variable. Okay. So on our warm-up, it says find LM. So when I'm done here, I want to find what this length LM is. And we're given opposite sides, which we know are congruent. So we can just say that 6x equals 5x plus 4. Okay, that these sides are congruent. And subtracting 5x, I get x equals 4. And I'm celebrating because I'm solve for x, but I wouldn't get full credit here because it doesn't ask for x. It asks for LM. So x is 4. I now need to go in. LM is 5x plus 4. So then LM would be what length? 24. Okay, so we want to make sure we respond to the actual, question. Sometimes it just asks for x. I think your checkout just asks for x. Other times it asks you to then find a piece once you find x. So same idea on the second problem here. It doesn't just ask me to find x. It says find the measure of angle t. And this one's a little trickier because t isn't even a part of where our variable is. It wants me to find the measure of that angle when I'm done. Now what I am given here are opposite angles, right? And what do we know about opposite angles? They're congruent. So this angle is the same measurement as this angle. So I can say x plus 44 equals 44 plus 2x. Or subtract x, 44 equals 44 plus x. Subtract 44, and I get x equals 0. Now I'm not done here. I now need to find angle T. Well, if x equals 0, what is angle U and angle S? 44, yeah. If I plugged in 0 here, I'd know that this is 44 degrees and that's 44 degrees. What is the relationship between both U and T? It's the same relationship as S and T. What needs to be true here? Yeah, they're adjacent angles, so it needs to add up to 180. It needs to be supplementary here. So if this angle is 44, then this angle must be what? 136 degrees in order to be supplementary. Or angle T equals 136. On our third example, same idea basically as the first one. So it asks me to find QR, which is here. I'm given opposite sides, which I know is congruent. So 2x subtract 3 equals x plus 7. Or x subtract 3 equals 7 and x equals 10. If x equals 10, what does QR equal?
17.
QR equals 17. All I did was plug that in. 2 times 10 is 20, subtract 3 is 17. And 4 is a little easier than 2 because it gives me an angle that I already have. And I think it's the same problem as above. Like it's x plus 44 and 2x plus 44. It looks a little different angle, like the T and V are the ones that are opposite. But it's the same setup. So I get 2x plus 44 equals x plus 44. And when I solve, I just like on number 2 get x equals 0. If x equals 0, then what is angle V? 44. Okay, good. So these properties, all of these properties we just used, that they're true for all parallelograms. Okay, parallelograms is like, I think of it as like the great grandmother of all these other shapes. Okay, and all those other shapes inherited all of these traits that great grandma has. Okay, they get all of them. But within parallelograms, there are smaller categories of types of polygons. And so that's what we're going to talk about today. So in your notes packet, if you find notes number 2, we're going to talk about special parallelograms. Oh, interesting. We switched the order of units this year. I don't think we've done that, a property that we need. Maybe we have. I don't know, everything's blending together. You can tell me when we go over it. Okay. So what happens when you rearrange a class? You find things like this halfway through. So one special parallelogram is a rectangle. A rectangle means we have a quadrilateral with 4 90-degree angles. Okay, or right angles. That's what makes the parallelogram into a rectangle. Instead of kind of being tilted over like we saw those parallelograms, everything is square, 90-degree angles. Now, why is a rectangle a parallelogram? Okay, how do we know that it's a parallelogram? Well, in our rectangle, we knew since, first grade that a rectangle opposite sides are congruent. So that's true. Opposite sides are congruent and parallel, right? They're never tilting at all and going to intersect. That's enough to know that it's a parallelogram. But given that all of the angles are 90, we can also say that the opposite angles are congruent. Okay, opposite angles are 90 and 90. And 90 and 90 add up to 180. So the adjacent angles are supplementary or equal 180. So, like I said, parallelograms are the great grandma, or grandma, of these special parallelograms. The rectangle, which is lower in this kind of family tree, is going to inherit everything a parallelogram has. Okay, this is the stuff that the parallelogram has. Now, with our diagonals, the diagonals are still getting bisected, but something unique happens, okay, with our rectangles. Okay, so one thing that happens with our rectangles, just for a rectangle, meaning unique to the rectangle, is that the diagonals are congruent. Okay, plus still true that they're going to bisect each other. because that's a parallelogram property. So what ends up happening is I still have I can draw a diagonal just like I could on my parallelograms last class. But those diagonals are the same length, and that's because this, like if I look at half a rectangle, it's a right triangle. And that right triangle has, if we think about right triangles, you can use the Pythagorean theorem, right? So a squared plus b squared equals c squared. So it has like this side length and this side length. This other right triangle has the same two side lengths. So this, or sorry, I should go this way. This other right triangle has the same two side lengths. So this hypotenuse of those right triangles is going to be the same length. Okay, so my diagonals are the same length and they're being bisected, which means I'll use just a different color, that this and this length are the same, but because this diagonal is the same length as this diagonals, you end up having 4 lengths that are the same. Okay, so I'm going to put a point here and call it X. What ends up happening with this is you get 4 congruent parts. So it's being bisected, but because it's the same length, all of these end up being the same measurement. So AX is equal to CX is equal to BX is equal to DX. Okay, they're all the same length. If this is 5, that's 5, that's 5, that's 5, all the way around. Now this is the piece, and we use it a lot. So we're just going to introduce it now, I guess, if it hasn't come up. I think it comes up, I think we do it in the congruent triangles unit, which is our next unit. And like I said, we had shifted some things around this year to make the semester work a little better. But what we want to be looking for, maybe we've already done it. Okay, is what happens is we create these triangles, right? And so that triangle that I just highlighted is the same as this triangle. All 4 of these triangles aren't exactly the same because these lengths, A, B, and D, C, are different than these lengths. Okay, so this triangle is identical to this one because they have this longer length and then the 2 sides. This triangle over here is the same as this one, okay, because they have the same outer side length, okay? But beyond that, what I really care about is that because my diagonals create all equal parts all the way around, I get an isosceles triangle. And if I have an isosceles triangle where 2 of my sides are the same, like I do here, then the angles are the same. And I don't think we've talked about that yet this year, have we? Added that property in, so we're just gonna add it right in here. Okay, so what that means is I'm always going to have an isosceles triangle because of this special diagonal thing with the rectangles, which means this angle here and this angle here will also always be the same measurement. Okay, that this angle and this angle will always be the same, and same here, that this angle and this angle will be the same because it's going to break apart 90 somehow. It's not going to break apart 90 evenly. So then what happens is I have these other triangles on the other 2 sides of my rectangle. And same idea, they have isosceles here. So I know that this angle and this angle are the same. And then same over there. That's a super important thing to know about rectangles because it's going to allow us to find all these smaller pieces of the angles that it's going to ask us for in problems. Okay, so if 2 sides are the same, then the 2 angles are the same, the 2 base angles. And if you think about what we just did on our test, where we ordered sides and, I want like a scrap piece of paper, where we ordered sides and angles. And we said the smallest side corresponds to the smallest angle, the longest side corresponds to the largest angle, where we did this. Like, let's just say that this is 5, that's 7, that's 9, A, B, C. So I said, oh, C is the smallest angle. 7 goes to A, would be the middle angle. 9 goes to B, that would be the biggest angle, right? We just did that in unit 4. So then it wouldn't be too much of a stretch for me to say, well, if both of these are 7 and then that's 5, well, then we would go, well, this length and this length are the same. So this angle and this angle have to be the same, okay? Does that make sense why that happens if you go back to unit 4? And that's what is happening in my rectangle is I have this rectangle and I have these diagonals and we know that these sides are the same. So again, if I pretend that's 7 and 7, then these bottom angles have to be the same measurement. There's no way to order them because the lengths are the same. Okay, so that's what's happening there. And it is super important when we get to some solving pieces. Okay, so that's our first like little baby of grandma parallelograms is our rectangle. We also have a rhombus. That's a special type of parallelogram. Now a rhombus, when you're like 5, is sometimes called a diamond, okay? But it's not a diamond, it's a rhombus is the term for a parallelogram with 4 congruent sides. Now notice I say 4 congruent sides, I didn't say anything about the angles. Many times when I say, what's a quadrilateral with 4 sides the same, people say a square, yeah. And totally, we're gonna get to squares in a minute, okay? A square has 4 sides the same and they're all squared up. They're all 90-degree angles, okay? A rhombus doesn't have to have that 90-degree angle part. It's just all 4 sides are the same. So every rhombus is a parallelogram because, well, the opposite sides would be congruent. And that's enough to prove that something's a parallelogram because they're all the same. Well, the opposite ones are also the same to each other. Okay, that's enough. I listed them all up in rectangle, but that's enough to know. And so therefore, all parallelogram properties apply, okay? If we know a rhombus is a parallelogram, everything we know about parallelograms is still true about my rhombus, okay? That my opposite angles then are congruent, that this has to add up to 180. I'm holding off on marking it because I want to mark it special when we get to this next part. Now, our diagonals for a rhombus, they're still going to do this. Bisect each other, okay, which is a parallelogram property, right? So all those properties are still true. So I want to draw in my diagonals. Let's not draw anything on them quite yet. They're not, this isn't a rectangle, so they're not all the same. The parallelogram property is true where it's bisecting that diagonal and it's bisecting this diagonal. Okay, not necessarily the same length all the way around. What is special? Okay, so this right here of the rhombus, this is unique to rhombus. Okay, this is only true if we know it's a rhombus. Then we also know that the diagonals of our rhombus are perpendicular, which means 90-degree angles in the center. And that then, this one's super important, all of it's important, that it bisects the opposite angles. So perpendicular means this, that this in the middle, that it's 90 degrees around here, which is helpful because I have triangles and that can help me find a missing angle sometimes. This is super important as well. We use this a lot. bisect opposite angles, meaning here's this diagonal, it's cutting these angles into equal parts. So what's here, it's also the same measurement over here, and that's the same on the other side, okay? So it's cutting these angles into an equal amount on both sides. And it's this other diagonal is going to do the same thing. It's cutting it into the same amount. Now, they're not all the same, right? These angles are the same, so they're cut the same. These angles are the same, so they're cut up the same. Okay. Such a bummer. I really wanted to talk about squares, but it's just there's so much excitement involved. I don't possibly have enough time to talk about it. Yeah. You know, it's like too good that I can't cover it in just a couple of minutes. So what we'll do, I didn't get as far as I wanted to today, but just kind of hold on to these notes. Tomorrow we're going to continue